Hello everyone, we will continue with testing of fiber parameters. In last few classes, we have discussed about the measurement of fiber length and the distribution of fiber length. We have discussed the measurement techniques of fiber fineness, and also in last class we have discussed the maturity. Now, we will continue with the measurement techniques of fiber, and this technique are at present what we will discuss the two commercial instruments where only cotton fibers are used, and these instruments are not for a single parameter. In these instruments we measure the large number of combined parameters, okay. And these are very fast, it is not slow, it is a large volume of fibers can be tested. These two equipments are, it is a combination of test methods, combination of parameters are testing. This is one is HVI, high volume instrument, and AFIS, advanced fiber information system. Both these instruments are basically used for cotton fiber testing. Now, first we will discuss about the high volume instrument testing. This high volume instrument system measures various physical characteristics of cotton fiber. In last segments, what we have discussed, like for measurement of fiber characteristics, a particular technique used for a measurement of a particular characteristics. Okay. But here in high volume instrument, it is a combination of instruments which gives a overall characteristic. It is not the single instrument, it is a total system. That is why we call it as a high volume instrument system. Okay. This is the combination of systems where we take the principle of earlier methods, but like for example, in HBI we test the fiber length exactly same as that fibrograph. Similarly, the fiber fineness we measure here exactly same as the airflow method. So, that way it is a combination. So, in high volume instrument we test fiber length, length uniformity. So, fiber length and length uniformity we measure by fibrograph method. Strength, it is a bundle strength we measure here, strength and elongation in bundle form. Micronear we measure, color can be measured here, and trace percent, trace content can be measured, okay, and even maturity can be measured. Okay. So, all these parameters are measured here, and the advantage of HBI is it is a very fast method, okay. It is a quick method. So, that large volume of fiber can be tested. Now, the length, the measurement technique we are not going to discuss here, because it is exactly same that we have discussed in fibrograph. Now, length data, that is the average fiber length based on the fibrogram principle of measurement of fibers. Okay. This is the same principle. Here also we measure the upper half mean length and span length. The mean length of fiber divided by the upper half mean length, we get the uniformity index, or the uniformity ratio we can measure. So, these things are exactly same as the that we have discussed earlier. Strength is measured in the, that is the, it is a force required to break the bundle of fiber clamped by the combing device. So, the same clamp is used which is used for fiber length measurement. Okay. The same clamp, here only the fiber is broken and the force required is measured. Okay. By measuring the breaking force and taking the mass of the fiber, we have to take the mass of the fiber bundle, and elongation is measured, the amount of stretch which a bundle of fiber incur prior to break. So, before breakage the amount of stretch is measured. Okay. Then microneer, an indicator of the fiber cell wall thickening and parameter. Okay. So, that is the microneer value, which is actually indirectly, it says that it indirectly measures the, that is maturity also. That is why here only it measures the microneer, but it says that it indicates the maturity of fiber also. And microneer is an estimation of fiber fineness, it follows the airflow method here. Short fiber index, and this is its index, the index shows that percentage of short fiber in each sample tested, okay, test specimen. Short fiber for cotton are defined as the fiber, all the fibers less than half an inch, okay, or 12.7 millimeter. So, after this fiber length test, one can get the short fiber percent. So, that is all fibers by the less than half an inch, that we have already discussed. And HVI can also measure the color grading. Okay. Color grading is the, in terms of two parameters, one is the reflectance and yellowness. Okay. That actually colorness, color grading is important, because it depends on the, depending on the color grading, the price also changes, and it also shows the, to some extent, the quality, overall characteristics of cotton. Okay. And how, what will be the actually ultimate fabric characteristics, fabric color it shows. Another parameters which it measures, it is a trace content, and here trace content is measured by video scanner, because that fiber, raw cotton fiber, the video scanner actually it measures the area covered by the trace. The trace in raw cotton is measured by the video scanner, commonly referred to as a trace meter. Okay. Trace meter is nothing but a video scanner, where it senses the presence of any foreign particle. Okay. It measures both the leaf and other elements, okay, such as trace particle, grass, bark, anything other than cotton. It measures the actual area present as compared to the total area of fiber. The surface of cotton sample is scanned. So, any material, any trace present inside the fiber mass will not be actually measured here, but here the assumption is that the trace particles are evenly distributed. Okay. The surface of cotton sample is scanned by the scanner, okay, by the camera, and the percentage of the surface area occupied by the trash is calculated. So, if we know the area total and then you add the total area of the trash particles or foreign particles and compared with the total area, and then we can calculate the trash content. From all this data, all the trash length, strength data, we can predict the spinning consistency index, and here an index which indicates the spinnability of cotton based on the formula incorporated, okay, which all the HBI data, it incorporates all the HBI data. So, that and this the formula, this equation, empirical equation has been developed based on the large number of data. Okay. Now, this is the spinning consistency index. The higher value shows the better spinnability. Okay. That means, we can see the strength is in the positive side. That means, if strength increases, the spinning consistency index will increase. That means, spinnability of the particular fiber will be better for if it is stronger. Okay. Then, if the fiber is coarser, that means micronear value is more, the spinnability will be poor. So, that means that is why it is in the lower side, okay, the minus, okay, negative side. So, spinnability is indirectly it is negatively affected by the micronear value. Then upper half mean length, it is a positive impact. So, we can see the impact of length is maximum as far as spinnability is concerned. Spinning consistency index is concerned, its coefficient is 49.1, very high coefficient. So, that from here we can actually get the impact. Okay. Then uniformity index, so it has got positive impact, we need higher uniformity index, then RD value and then Eolanese value. Okay. So, this from this we can, if we know all this. So, this instrument measure, after measuring, recording all the data and automatically calculate the spinning consistency index, and it will show that the spinnability of fiber. These are the value, and also it can predict the CSP from the fiber. Okay. That count strength product can be predicted here, an index which indicates the predicted ion breaking strength based on the formula is using the HBI value. So, HBI value, if we take all the HBI value, that micronear and this strength, everything if we take, we can get the CSP value. Okay. So, MIC is micronear value, length, uniformity index, reflectance, brightness, elongation, strength if we take, and if A, B, C, D, E, F, G, H, G, all these things are the coefficients. So, one can actually for a particular type of fiber, particular and CSP here A, B, C, this coefficient are not fixed, because this CSP also depends on the twist or different on machine type of machine and all this. So, for a particular industry, when they are using this HBI data and they are getting the CSP, they can actually develop this equation for their particular machine. Okay. This A, B, these coefficients are dependent on the machine condition, the type of twist level and all this. Okay. Now, the applications, what are the applications of HBI data? Who are the people who use this data? The cotton seed breeder. Okay. How do they use? Verify the progress in attaining the goal in developing of a new variety of cotton. In the cotton research, that they use. So, they develop cotton and then they measure. Okay. Cotton producer to know the grading of cotton, what is the grading, and they can get the market price. Cotton merchant and consumer, obviously they would like to know the cotton classification of cotton, they would like to know the quality of cotton and to assess the yarn quality. And cotton research, basic research and investigation of various physical properties of textile fiber one can measure. Okay. Now, coming to the next set of instrument, which is AFIS, Advanced Fiber Information System. Okay. This Advanced Fiber Information System is that it is based on aeromechanical fiber processing. What is aeromechanical fiber processing? It's just like a carding. Okay. We take the fiber mass and by like it's a carding, it opens the fiber, it individualizes the fiber, and then the individual fibers are transported through a sensing device. Okay. Similar to opening and carding, followed by electro-optical sensing and then by high speed microprocessor based computing and data report. So, after sensing, all the data are actually that computed and then reported. This is the schematic diagram. The sample, then aeromechanical separator, that is then electro-optical sensor, central processing unit, then it is a data. Okay. So, this is the typical process, and the components are a motor or blower, lint waste box, control system or control board, that is monitoring, controlling and connecting. Then it is a fiber individualizer, the fiber to individualize the fiber, and we need a software. These are the different components. This is the basic schematic diagram, okay, general schematic diagram. Here the fiber is fed here, okay. That is normal, like in carding we feed. This is the feed roller, through feed roller and feed plate the fiber is fed here, and here it is a pinned perforated cylinder which actually opens the fiber against the flat, okay, AFIS flat. So, against this flat its fiber gets individualized. Okay. These are the stationary flat. Okay. The individual fibers are carried away by this pinned cylinder, and from here it is transmitted to the another cylinder opened fiber, individual fiber. There is a stripping action is there. This is transferred to the another pinned cylinder, and from there fiber is passing to the sensor. Individual fibers are passing to this sensor and trace particles are separated. These trace particles are separated. The fibers, the individual fibers are moving here. We are not talking about the large number of cluster of fibers, which high volume instrument deals with. The high volume instrument, the difference here is that in high volume instrument we deal with the cluster of fibers at a time, be it in fiber length, fiber micronear, fiber whatever may be, but here it measures the individual fiber. That is why using the pinned cylinder fibers get individualized, then fiber one by one fibers goes to the sensor, and the trace is totally separated here. Okay. Now, this is the fiber sensor. From the sensor, single fiber is, so from that equipment, from the pinned cylinder, this single fiber is coming. Now, here it is a source light and it detects the total fiber characteristics, fiber length. If we know the speed of flow and time required to cross this line, then it is basically we can calculate the length and the direction of flow. In such a fashion, fibers will flow in a straight line, and that is why this is the conical method tube which actually ensure the straightening of fiber. This is similar to that transport tube in rotor spinning. Okay. This is so this fiber moves in straight fashion, and here the light scattering technique is used to measure the diameter and also the shape of the fiber and the time required, and if we know the speed of the fiber and time required to cross the line, it will give us the idea of the fiber length, okay, considering that fibers are not the crimped, and we get the Aphis, and this is the normal fiber. Okay, this is normal fiber, that the waveform, and if the fibers are in the nape form, we get this type of peak. So, we can get also in Aphis the nape content. Okay. So, the number of this type of peaks gives the nape content, okay, and this is the. So, we can easily separate out the normal fiber along with the nape, and also as it is a light principle, here we can calculate the diameter of nape. So, Aphis length data analysis is very exhaustive, from there one can get. So, once it is tested, data, all the data are recorded. So, one can easily analyze the data. Now, Aphis data analysis is very important. Now, we will see the individual type parameters, how the data is analyzed. Now, the napes, what is that? Definition is that it is a fiber entanglement. So, as per the Aphis, whatever entanglement is there, it will term as the nape. Okay. Irrespective of the definition of nape for other part, it will actually term the classify the fiber as a nape if it is entangled, any entanglement, and it causes imperfection of yarn and fabric. So, we will get idea about the level of imperfection in the yarn from the fiber data. Okay. Nape count, number of napes in 1 gram of material. So, if we test the, if we know the amount of material, so then we can calculate the nape count. So, it measures the number of nape. Okay. So, quality level, nape size. So, it measures the size of nape also. So, nape, the average diameter in micron. So, it measures the size of nape and determines the impact on yarn and fabric. So, if we know the size of the nape, so it can, we can predict the what will be its impact on the appearance of yarn or in fabric. Okay. Count of nape, or so coefficient of variation between the samples. So, that CB% of nape we can measure, okay, and from there we can calculate nape removal efficiency. So, if we take suppose in carding or for any method, before carding and after carding, if we measure the, so input minus output divided by input multiplied by 100 is, it gives the idea about the nape removal efficiency. So, just we can try to see here, only if we get the nape data, we are able to get so many parameters, okay, and we can predict the actual appearance of the actual quality of the final product. Similarly, we can see the length and diameter data. Nape is separately measured because of the signal, okay, Now, length and diameter they are measured simultaneously, because when fiber is moving straight way, in that case length we can measure. Length is in terms of mass we can measure, because we know the what is the mass we have fed in the machine, because nothing is going waste. So, in terms of mass, the mean length by weight, if we know the mass and if we know the individual fiber length. So, it is comparable with the HBI 50% span length, that we can compare, that is mean length by weight. Then we have the fiber length of individual fiber length of, then we can measure the CV percent, CV percent of fiber length, but CV percent of fiber length we cannot measure in other technique, because other technique we can measure the variability in other way, that we have seen uniformity index, uniformity ratio, but here as we have got individual fiber length, we can calculate the coefficient of variation of fiber length by weight distribution. Okay. This is actually we can predict the spinning performance of and the yarn quality. Okay. And also as we have the number length of individual fiber, we can also calculate the short fiber content. The fiber by on the weight basis, the length which is less than half inch. So, we can do this is comparable with the short fiber index of the HBI upper quartile length, because we have the fiber length. So, we can measure the upper quartile length, it is a top 25%. Mean length we can measure the calculate the mean length and coefficient of variation of length. Okay. That is, this is in the terms of number. Here it is important is that in AFIS we measure the individual fiber. So, that means number is there. So, we can calculate on the basis of number also, short fiber content in number in terms of, and 5% in number and 1% in number also. This is important for machine setting. It is a longest 5% of fiber length, okay, by number, longest 1% of fiber length by number. So, this will give us the idea about the machine setting. We can get the help with the using the fiber length. So, we can use either 1% or 5% for machine setting. Then coming to the diameter. So, as we can scan the fiber, total fiber, the length as well as the diameter can also be measured. Diameter of individual point, not the individual fiber, individual point is recorded. Okay. Average diameter of the fiber by number can be measured, because we know the diameter. So, mean diameter can be micronear estimation. Here we do not measure micronear, we measure directly the diameter, because it is a light scattering, Light's principle, and coefficient of variation in diameter. We have the individual data and then we can measure the coefficient of variation. It estimates distribution for micronear or denier. Okay. That is the, and length by number, it is the length of individual fibers. These categories are added together, okay, to obtain the length measured for short fiber and average the mean length. So, that we have the individual data. Length by number measurement is not influenced by the weight. Okay. Weight it is not influenced, because it is a individual data, individual number is there. In textile processing, it is recommended that the length by number be used to determine the machine and equipment setting. That is why we have actually seen here for equipment setting, it is 1% by number, 5% by number is setting. It is not by the mass, 1% by weight, by 1%, 5% by weight, it is not used. Also to determine the fiber damage as representation of short fiber percent. So, if we want to measure the fiber damage, it should not be by mass, it should be by number. Okay. For 100 fibers, how many fibers are got damaged? Because if the diameter changes, then the mass will get complex. Okay. So, that is why we must get idea about the number, because AFIS they measure in terms of actual individual fiber. This is the length data, just this is the by number, length by number. So, in y axis it is a length, okay, and x axis it is a cumulative frequency. So, suppose in this picture, so the 30 millimeter length, the cumulative frequency is this one, okay, like 20 millimeter cumulative frequency is say this is say 25% like this. This is the cumulative frequency. Now, from this cumulative frequency one can easily form the staple diagram. If we know the number of fibers for a particular length, then this is the what about this staple diagram? Staple diagram is nothing but the number of fibers in a particular length, which is arranged in from the descending order. That is what here all the individual fiber lengths are available. That is why it can predict the staple diagram also, which is not possible in fibrogram or HVI, because HVI and fibrogram we do not get the exact length, actual length of fiber. Here individual length of fiber is there, that is why we get, and from there we can also analyze the fibrogram diagram, okay, so staple diagram. Okay. So, if it is asked which instrument among AFIS and HVI gives the idea about the staple diagram, it is the AFIS, okay, because we get the individual length. Now, trace data analysis. So, here one sensor measures the fiber length, fiber characteristics, and there is another sensor which actually counts the trace particle. So, trace is separated in other direction, total count. So, individual trace is counted. When trace is getting separated, number of trace, all particles are counted, overall trace level by optical sensor. Okay. Trace counts all particles larger than 500 micron. So, total count is total number of trace, and trace count is actually it is all trace particles, it is a more than 500 micron. Here the trace is divided into two distinct way. One is larger particles are known as trace, and another particle which is dust. Okay. Trace, because larger particles always have tendency to remain in the with the material, okay, but dust gets separated. So, dust particles are defined as the particle, all the particles less than 500 micron diameter. This is dust analysis, dust removal analysis one can do. And total foreign matter, okay, calculation of total foreign matter, okay, and size, average size of all particles in micron. So, that if we can measure the by light principle, then we can photoelectric principle, then we can measure the size also. So, here it gives the total idea, but in that and in HVI or other method, those measure the trace in on the surface, okay, but in AFIS method it measures the individual trace. So, actual number of trace can be calculated, because fibers are totally individualized, and this is the trace data analysis, individual trace. So, we can get with this curve, we can get idea about the distribution of trace of different size, okay, we can take action on that. And this is the trace data analysis. So, here the trace counter, trace and dust as are coming, this is the, this sensor is for fiber, the two different sensor, and trace is getting separated from here and from this portion, and they are transported through this pipe, and it is again it's this is the sensor, the trace counter is there. Okay. And AFIS fiber fineness is again based on the optical measurement of single fiber, that is diameter, and multiple light scattering angle is allowed to determine the actual shape that we have already discussed. Actual shape can be measured, and if we know the actual shape, then we can measure the degree of thickening. The average fiber fineness, that is FIN, it is expressed in terms of millitex. It is 1000 meter of fiber with a mass of 1 milligram. Okay? That is called 1 millitex. So, if we can measure the mass, then we can measure the fiber fineness. Okay? And in the textile industry, the following classifications are measured: less than 125 millitex, it is very fine like that, okay, and more than 250 millitex, it is a very coarse. So, it measures the fiber fineness. And now we will end this session. Thank you.